My name is Yildiz. I'm a postdoctoral researcher at the University of Tübingen, and I have my PhD degree from Aalto University Computational Systems Biology Research Group. So there I work with Harry Lattes-Maki and Marcus Heinonen. My research was mostly focused on neural ODEs, you could say, which may sound scary when you first hear. But today I'll try to walk you through the neural ODEs in a more gentle, slow way. So basically, neural ODEs, like one sentence summary of neural ODEs would be an ODE system where a differential function is a neural network. And like ODEs, I think the first ODE was proposed something like 350 years ago, like even before, like Newton and Leibniz, they were like introduced, the first ones. So that like the theory theory behind ODEs is quite, like well established, and it could be a bit tricky to understand, at least for machine learning people, including myself. So today I'll be mostly focusing on machine learning aspects rather than the theory itself, which I hope will be useful for you as well. So unfortunately, I need to zoom in a bit. Like this is the first half of the lecture. So basically, we will have 6 sessions. In the first one, I will formally describe what ODEs are, and like I will introduce terminology like ODE solutions, numerical solvers, and blah blah. And we will have a simple example where I hope that you'll get an intuition about ODEs. And then in the second part, we will define what neural ODEs are, and like it'll be smooth, I promise. And we will simply see like maximum likelihood estimation type problems with neural ODEs, because these are probably like the easiest ones to start with, right? Yeah, and now we will go into like we will have like a more of a variational framework where we will introduce latent Bayesian neural ODEs and like a variational framework as well. So it matches like this workshop or this summer school nicely. Then we will have a long break for 15 minutes. This one, go. Then we will completely change our direction into classification. That's right. So I'll basically prove that like all the fancy neural net stuff, they are nothing but neural ODEs. And after that, I'll talk a bit about continuous time normalizing flows, which Didik already like did yesterday, and like I think he's not here, but he made a really nice talk yesterday, and I hope that like the foundations of normalizing flows will be like there already. And then I'll introduce a bunch of new papers, new stuff around neural ODEs, like extensions or papers that handle different like problematic aspects of neural ODEs. And then we will end with a summary and Q&A session. Like ideally, after each section, there will be a short break, just short, somewhere between 5 and 7 minutes. And there are either simple assignments, I mean assignment in the sense that like go through this material, like check out the code type assignments. I guess there is no coding at all, but of course you are welcome to implement stuff. Or you could just like read the material again so that ask questions. Yeah, I think we can get started. So what else? Yes, and there is, okay, maybe this is like the most important disclaimer. Like most of the stuff included here is from the original neural ODE paper or like the corresponding GitHub repository. By the way, neural ODEs, they received Best Paper Award in NERDS 2018, I think. And ever since there's like a huge, like buzz around neural ODEs. But I mean, you'll see that they're not special at all. And what else? Yeah, there is a lot of implementation involved. And like, I hope that the code in the notebook will be understandable, but there's a lot of behind the scene implementation that you should have access to. These are like separate Python files. Yeah. what else? Yes, then we start with like one big cell, which is like if you can execute this cell nicely, then it is supposed to like install and import all the necessary libraries like torch and maybe this is an important one, torch, diff, torch differential equations, and the others are like pretty standard. Yeah. Okay, ODEs. ODEs are simply equations that involve one independent variable, one or multiple dependent variables, and their their derivatives. So here in this like simple example, the independent variable is time, the dependent variable is x. In this throughout the tutorial, time will be the independent variable, but this is not like mandatory at all. So we will say that x is like some quantity of interest that we like observe. Let's say x could be the position of a certain object, that could be the position of a planet, and xt would mean like where the object is at time t. And x dot t is the time derivative of x, time derivative of, so I'm going to refer to x as sometimes like state. So x dot t is the time derivative or just derivative. And like this is one notation and that's the other notation. And basically derivatives are defined as the limit here. So what the limit says is that like what if I take time to like an infinite small amount like forward. So you just change time a bit, and then this quantity, overall quantity, would tell you how the state would change if I change time, just time amount forward, right? And of course, the formal definition holds in the limit where delta t goes to 0. But we will see that like we will have a bunch of approximations all over the place where delta t does not go to 0 at all. Now, all of these expressions are going to be equal to one function, which is shown on the right-hand side. So here f is called the differential function, or sometimes I'm going to call it time differential, sometimes right-hand side, sometimes vector field. Like people with different background, they use different terms, but there could be slight differences as well. But here they're all like synonymous. And now we say that time derivative of x is a function of x itself. So like how x would change over time is a function of x. That means like how the, let's say, how the object is going to move, or like in which direction it'll go, is a function of its own like location, let's say. And U2 is like some external control signal. Let's say like you're pushing a car, and then U2 could be like how much force you apply. And T is, well, time. Yes, and throughout this tutorial, I will skip UT. So there will be no force, no external control signal, no action. Again, like almost the same stuff. So they won't be there. Yes, and this is going to be our main, well, let me go up a bit. So this is going to be the main equation that we will have. So next state, like, say, so whenever you have whenever you have differential equations, like time or like independent variable becomes continuous, right? This is unlike the autoregressive or discrete stuff. So that means there is no concept of next state here. But I mean, you could say next state definitely is equal to the previous state plus like some update factor like delta t and the vector field time differential. And this holds again if delta t goes to 0. That's the formal definition. Yes. Now, more terminology. I'm going to often use the term called state solution. So here, xt is a state solution, OD state solution, OD solution, and it is defined as this like right-hand side, where we have one initial value, x0, and then we integrate from time 0 to time t. Like this is where we start, right? So this should be like the lower limit of the integral, and until time t, we compute the integral, right? And like t is there. And inside the integral, we have vector field. We have a differential function. Now, if f of x is equal to x, right? This is like super easy to compute. If f of x is like constant, that's also easy to compute. Like remember the high school calculus formula. But if f of x is a bit complex, then solving this thing is usually like almost always quite difficult. And a spoiler, in the future, f is going to be a neural network, right? So we will compute like an integral of a neural net in a sense. And typically, like the problems that we are going to solve, they will involve one initial value, x0. So this will be like almost always given. And then we will have a bunch of time points, like a set from t0, like t1, and all the way to tn. That means we will be often interested in solving the state solutions at the given input point. So at these points, the state solutions will be like these things here. And again, like more notation, x0 to n means like this guy over here. This is like the set of state solutions at the input points. So like you might be overwhelmed, but these things will be clear. Yes, so like typically computing this integral is difficult, and what we do is we use numerical solvers. And like there's a whole literature which I barely understand, so I'm not going to go into the details. But in like take-home message is that we have those things called numerical solvers, which give us the state solutions like with certain guarantees. So like we could control how much error. So whenever so computing this integral exactly is almost always impossible. That's why we approximate it with numerical solvers, and because of that, we make some error. And the error that we make, we can control. So that's a nice thing. Yes. So after a lot of mathematical stuff, let's see a few examples. So now we will have a really simple two-dimensional ODE system called one-dipole oscillator. So like a two-dimensional ODE system means our state vector x has two components, which are x1 and x2 here. And all I do is I specify the time derivative of x1 and x2. So this thing over here, it says how x1 and x2 would change over time, right? And basically that's a function of x1 and x2. If you look at the right-hand side, like you see like some relation between x1 and x2, right? So it means like how x1 would change over time, like is just equal to x2. And then there we have just a single parameter called mu, and that's it. So like the whole ODE system is defined in terms of whatever you have on the right-hand side of this equal sign and just one parameter. Okay, now finally, let's implement stuff. So our implementation will be based on Torch, which I hope you are all familiar with. And we're going to use a library called torch_diff_ec for, well, differentiation, computing the integrals. And like the way that torch_diff_ec works is that you need to define, like for each differential equation at hand, you need to define one class. Like here I define VDP class, that means one dipole. And it simply extends an end-up module. And then inside the constructor, well, I only have mu. There was one parameter in the ODE system, right? And it's in the constructor, we specified there. And then you define a forward function, which takes time and state as input. Like if I go up here again, so that's our differential function. That's our right-hand side, right? The forward function is going to implement this, and the signature will always be so that we first have time, and then we have state as input. And then inside the function there, well, all I do is to implement this thing over here. That's it. And I mean, the implementation is like super straightforward. Like the first component of the derivative is equal to the second component of the input. That means first component of the output, like this thing is equal to x2, which is the second part of the input, right? And that's it. Now, one nice thing with this library, or like with ODEs in general, is that if you have multiple ODE systems, you can compute them, like compute the integral concurrently. So that means the input, like you could integrate n different ODE systems in parallel, and each ODE system must be like of dimensionality d. And in that case, d is 2, right? And n will be arbitrary. Now here. Now finally, I will show you like some figures. So first, like let's see what one dipole system looks like. For this, we first create the one dipole system. So like the only parameter that we have is equal to 1. And then we create an initial value, which is for some reason 1 and 0. Again, like in 2D, we have a single point, 1 and 0. And then we say like a bunch of time points, which are between 0 to 15. And we have like how many? 500 of them. So we will compute all these solutions at 500 points, starting from 0 and ending at 15. So that's all you specify. And then you just call this ODE function, which performs integration. And now there, the first function, the first input is the ODE system, one dipole. The second input is the initial value, and the last input is the time points. And the output is like of shape t and n, where t is the number of like the length of the trajectory, which was actually specified here. So it'll be 500. And n, capital N, is how many trajectories you compute in parallel. Here it is 1, because we only have one initial value. And also n, small n is 2. Now let's run this cell, which I did for you. Now I need to zoom out, but did I zoom out or zoom in? Yes. Now, here's a simple animation of the one dipole system. On the left, I showed the first state, x1, against second state, x2. And on the right, I show you both states plotted over time. Okay. And on the background is the vector field, like differential function. So the value of the differential function, let's say at this particular point, is this arrow. And as you can see, like when I compute the integral, it's always that the trajectory, it follows the vector field. So again, all I did was I created one like class that implements the OD right-hand side differential function, and then integrated, and then magically, like it gives us this trajectory. So that's practically how ODs work. Question, yeah.
Is used in your code because this equation doesn't take t as a parameter. So if you change t, how will it affect the code?
You mean which t? The one like up there, like the center. Okay. Let's do it this way. So I start from here. This is like the initial value where time is 0. And then I compute the integral, let's say from time 0 to time 1. Right? And then it would be like I would start from here and reach all the way, let's say there. And then if I compute the integral from time 1 to time 2, then I would end up there. And then from time 2 to time 3, the trajectory would just continue. Did you see what I mean? Let's stop the animation for a second. So that's now the state trajectory until time 1.2. So if you start from here and then integrate for 1.2 seconds, this will be the resulting trajectory. So basically, let's go up there. So if now this t is 1.2, then the result of this integral, like this guy over here, would be this particular point. Did you see it?
I see that, but in the equation class, you have only mu. You never pass t.
T is passed into the ODE solver here. So like at which points we compute the ODE solution is not a part of the differential function. It is a part of like the whatever solution that's going to compute. So differential function, like the class implementation, it only looks at the differential function. So this thing. All right. Yes. Speak up a bit. Okay. Yeah. Now here we stop the animation, and there. You mean this one? I mean, now we will have a short break, let's say 5 minutes, where there is like I created one set. Like I'll take the questions off now. Where there's like one additional cell that you can play around with stuff. Like what you can do is you can change mu, the input, and like once mu changes, you'll see that the whole trajectory changes. You could like enter different time values. You can have like multiple initial values, or the initial values starting from like strange places, like in the state space. Just play around with it and then try to get familiar. I'll be walking out. I think we can continue. One like general announcement. So the material is like on GitHub, but there's a link to a OneDrive folder where like that's my folder. You can download the material and then you can run it like on your local computer, like on your computer. But I think there is no collab link or anything of that sort, or not yet, or maybe not ever. But just the same material. And one again, like general comment is that so far there is no neural network. So far there is no neural ODE, but only ODE stuff that we saw. Yeah, Ross.
Yeah, there. Key to
Yeah, there's a mismatch. Like the equation and the code, there's a tiny error. It's a typo. But I mean, it really doesn't matter. Like the implementation, the code here is supposed to match this thing. I have no idea which one is correct. I mean, the code should be correct because I know the figures. Then yeah, don't mind the equation, but the code is right. But I mean, this is just one particular ODE system that like I just showed you because I know it. But yeah. So okay. Right. And now we will move into neural loading. And so in the previous section, what I showed you was that once there's a right-hand side, once there's a differential function, then it maps to a trajectory, right? For each initial value, like let's say, for this particular initial value, the blue one here, we had one trajectory, right? And this is because we had a fixed form vector field. So maybe we could go into the other direction. That means, let's say we observe some trajectory. Let's say we do not that like the underlying system, what we observe is in continuous time. Let's say we like watch planets moving around, and then we would like to like identify the dynamics. So we'd like to know how the planets move, like what formula they follow, right? In that case, like we could use ODEs. So given a particular trajectory, can we learn the right-hand side? Can we learn a time differential function? So that's the whole idea. Now, if I give you this trajectory, And then if I give you, let's say, this equation, which is incorrect, then what you can do is you can like use certain like statistical, I'm gonna say like methods to infer mu, and that's it. That means like once I give you a trajectory and this fixed right-hand side, fixed form, inferring mu is super simple. I mean, well, I know that. But there are certain cases where writing down this equation, like here, is quite difficult. Let's say we have certain measurements from human cell, which is a complex mechanism, right? There's like a lot of interactions going on between like certain RNAs and proteins and stuff. And like we have so many of them, like so many different how to say like particles that interact with each other. It would be almost impossible to write down this equation. Like you just can't say this mRNA concentration affects this like other molecule like this and like that. That's not possible. So basically, then the idea is that like for those cases where writing down this equation, like the right-hand side is difficult, what can we do? And basically, the whole idea of neural logic comes from there that says like, if we have a bunch of trajectories and if we don't know what the functional form of the right-hand side time differential looks like, then what you do is you just throw a neural network and then you learn it. That's it. So this is going to be like the whole idea of like the one ahead of us. So let's be more formal. Let's say we observe a sequence here as I showed, y0 to n. So again, n plus 1 observations. And then let's say each observation yn is equal to some underlying state, xn, plus some noise term, like nothing special going on. But now let's say xn is like not just some, like not like any random variable, but let's say x of these xn is actually like the result of an integral. So that means like let's say we observe a continuous time system and we have measurements from there, but the measurements are noisy. I mean, we do not know that they follow like some sort of ODE where the differential function is called f true. So there's one true underlying that we don't know. And then the idea is like, if we don't know, why don't we understand? We just use a neural network, FW, W corresponds to parameters, right? And then it just matches F true no matter what F true is. Okay. So it could be like a super complicated function, it could be like a linear thing, we don't know. But I mean, we don't want to, like bother ourselves writing down because there's so many different alternatives, right? Like the planets or like the molecules could interact in so many ways that like let's completely sidestep this and let's just throw a neural net that would learn something. So this is like the whole idea. Now we go into neural load implementation. Again, the code looks pretty much like the same, wonderful. Again, our neural logic class, it extends an end-up module. And then inside we have our, this is not, okay, inside we have our neural net, or you could say just a multi-layer perceptor, right? Where like it takes d-dimensional inputs, again, these two in one case, and then like a bunch of layers, whatever, and then it outputs, again, two-dimensional thing. So here I have this beautiful function called OD right-hand side. Now, the signature should be familiar. The first input is time, and the second input is state. So this is the same signature that we had previously in one example, right? And all this OD right-hand side function does is to compute the output of the neural net. So again, OD right-hand side is indeed our differential function, right-hand side function. And all it does is to give a neural net output. And that's now this is the neural net is done. And now let's take one more function forward, which will be quite convenient, where the inputs are the time points that, like, as I said before, we have a bunch of observations like y0 to n, right? Let's say we know when the observations came. Let's say like we have observations from time 0, like time 1, all the way to time 10. So TS would be like 1, 0, 2, 3, like all the way to 10. And then x0 is like some initial value. Now, method is the numerical solver that we use. which I will go like the details will come later. And then all this forward function does is it computes the ODE solution. So this runs the ODE solver forward in time. Again, the inputs are the differential function, right? The signature should be time first and state second, and then initial value, and then TS. Now, yes, so again, just to match the equation with the code, but like once we run this forward function, then we would obtain x 0 to n. So again, the observation time y0 n, right? And once we run the ODE support, like once we run the neural ODE system, it would return us like like the same thing with like state solutions with like x here and here. That's it. And now let's see what is going on. Let's create a neural ODE system where the dimensionality is just 2. Like let's say again one initial value, whatever it is. Let's say like a bunch of points that we solve the ODE system, and now let's execute this cell, which I did. You will also probably fail. Yeah, let's execute this first and the second. Okay, cool. Now what I do is I solve the ODE system, which returns me one trajectory, which I just visualized there. So what I did was, it's an initial value, x0. Let's start integrating from there, and on the background is a vector field. It looks like nothing, right? Like really smooth arrows, and the vector and the trajectory simply follows the vector field. So it starts from here and then like goes this way because the arrows say like go this way. And as you can see on the right, again, nothing interesting is going on. And like even like the trajectory stops here, like over time, the states they don't change, right? And this is because here the arrows are small. The differential function value is small, just like. So now what happened is that we run the ODE, neural ODE system forward in time. We computed the integral, but with which neural network? The one that we created here, right? And what is special with this thing is, well, nothing, but it's just a one random neural net. Like however this sequence, like however this n dot linear creates the weights, it leads to this like silly, stupid trajectory. Like, and this does not look like one dipole at all. But now we will train the system, and then it will look like beautiful. So one question.
Yeah, it's just like this one. So I relate this. So we have the neural network has like random weights,
Yeah.
and then it's something in the torch effect that kind of enforces the smoothness.
No, it doesn't at all. Like the torch defect, all torch defect doesn't. It runs the numerical solver forward, and that's it. But it is like the way that the neural net is initialized is that it is initially smooth, and that's because how we like choose the weights. Yeah. Any question? Yeah.
So that means the new net, the single polar path to the net corresponds to a single time point in the differential equation. Single step.
So here basically we say that we would like to compute all these solutions at 1,000 different points. Can you repeat?
Values.
Yes.
Like a single time point x and t, and the polar path corresponds to just computing x t plus 1.
Yes, xt plus 1. But I mean, yes, that's right. And like it computes like initial x0, then let's say x like 0.01, which is like the state solution at time 0.01, then computes solution at 0.02, and then proceeds like that. But how it goes from 0.01 to 0.02, this is like integration, and this is implemented behind the scene. This is numerical solver. Okay. So finally, let's see the magic of neural ODEs. So again, this is our optimization objective. Again, we have a bunch of, like we have one input trajectory, y 0 to n, right? And then what we try to do is we try to learn a vector field, learn a differential function that gives us this particular trajectory. So what we do is we minimize, like this is like the silliest approach. We just do a mean, like define a mean square error between the data points and corresponding ODE solutions. And the corresponding ODE solution is given here. So yn, again, is the observation at time tn. And here xn is the ODE solution at time tn again. Right? So this ODE system would give us xn, and then we minimize this error. So if you do that, then you would learn a differential function that, like, once you integrate it all the way to tn, it gives you yn. That means once you integrate the trajectory, sorry, integrate the neural net, integrate the differential function, then it matches the observed trajectory. Now, something strange going on here, because once you compute the derivative of this whole loss with respect to w, now this term pops up. And basically, this is like the partial, or this is like the derivative of a state solution with respect to neural network weight. So like, typically what we have in like deep neural net stuff is that we have like one block, something fancy, and then the output goes into another block. This is like something fancy, deep, whatever, and then the output goes to next block, right? But I mean, here it's not like that. We only have one solver, like we only have one neural net that, like, you start integrating from x0, then like you integrate, it gives you, let's say, x1, and then you continue integrating, it gives you x2. Like you repeatedly use the same function, same neural net, fw, to move from x0 to x1 and x1 to x2. This is like a, you can say, recursion, or like in a recursive way. That's why you repeatedly apply the neural net, and you have no idea how many times you apply it. It's like numerical solver. It evaluates like the ODE as many, like whenever required. But I mean, anyways, so all I'm trying to say is that the gradient computation is tricky, but luckily this is already implemented in Torch Defect. And if you try to compute the gradients by hand, it's super nice that the gradient itself, like this guy over here, is given by another ODE system. So both like the state solutions is an ODE, and also the gradients are ODE, like they are given by an ODE system, which luckily is implemented. Okay, let's see one more example. So here, first I create some data. I have one dipole system. Again, like the mu is 1. I have 10 different initial values, so I will have like 10 input trajectories, all scattered between -3 and 3. And then I have 50, each sequence is of length 50. And then here I compute the ODE solutions, and then I add a bit of noise. So at the end, YVDP is my like data points. So there are like 10 trajectories of like 50, and that's my data. And here I show you three training sequences, which all like converge to the same cycle at some point, but all of them are noisy, right? So that they're imperfect. And these trajectories are totaled over time, like here. Now let's see how optimization proceeds. I hope this will make things more clear. And the way that I optimize is like sequences are of like 50, but I will take like subsequences, like you could say mini batches of length 10, because like if you work with shorter sequences, the execution is faster because you consider the state solutions like for instead of like computing a trajectory of like 50, you compute a trajectory of like 10, which is much faster. And that's why that's what I do here. So again, let's see the optimization code. Number of iterations, okay. Subsequence length 10. Like some optimizer, get a mini batch. And then here I call the neural ODE forward. Again, this forward integrates the ODE system. And again, I input the time points and the initial value, and then it gives me trajectories, right? Again, here, what I do is I have 10 input trajectories, and then all of those are integrated in parallel. So Xcent contains 10 trajectories of length 10, because I specify, let's make it this way. It has 10 trajectories of length 11 now. And this is the loss function that I had, right? Literally, mean squared error. And then backprobe. And what I do is in every 50 iteration, I'm gonna show you what the fit looks like. So let's run this cell. So red is an input trajectory, and blue is the fit of our neural ODE system. Initially, it was completely crappy. As I optimize, you see it gets better and better. So the trajectory would look more and more like the red, red trajectory surface, right? Yes, I think so far we had 250 iterations or so, and the fit already looks okay-ish. Like this is really crappy, but the right one is fine. But of course, the details are not very. So that's it. So again, what we do is, let me. Okay, I'm not gonna do it. So again, what we do is we compute an ODE, like we compute the integral to neural ODE system, which gives us one trajectory, right? And then we try to match this trajectory to an input trajectory. So let's. So how was it? He helped me. Okay, I did. Where do I define a neural ODE? Okay, here. So let's see it again. Again, blue trajectory trying to match the red one. And initially, the picture is as ugly as this. Like initially, the trajectory is like super, like nothing going on, right? As we optimize, it gets better. And all this is thanks to this like stupid mean squared error, like nothing Bayesian, nothing probabilistic going on at all. Yeah. And then finally, like I already did the training for you. And then, yeah, like once you train the system, you will obtain a picture like this. Fit is pretty good. This is like also over time I plot. There's like a little bit of lag there. This is acceptable. And now we will have another break. I'm going too slow. We will have another break where again, like you can just play around with the code, or you could like look into the edge joint stuff. Like again, as I said before, the gradients are given by another ODE system, which is called edge joints. I put a link there. You can just check it out, which could be difficult at this point, but yeah. So we'll be together in 5 minutes.
I have a question.
Yeah.
So here we're training, right? Just with the first 10 time points.
Not the first 10, but like any
Just like,
random 10.
so just like FNO, like you just take a trajectory, then you chop it, and basically
Exactly.
in this case 11 batches, and then you first take 11. Then
I mean, random, like completely random initial values could be like
Yeah.
the beginning, could be in the middle.
yeah, exactly. So then okay, yeah. And then the second point, right? This vector thing we have. That's basically the ODE, and that only depends on the ODE parameters. Let's say
Exactly.
the first example.
Exactly.
Yes.
I mean, it's just neural net weights that gives us a trajectory, like a whole vector is specified
exactly.
by W, but by
Yeah. But then already further question. In your paper, when you use this as a Bayesian neural network,
Yeah.
then the idea is right.
We'll just do it.
Great. Because then the idea is when you sample the parameters, basically you sample different parameters that will be east, then your vector will change.
Hey, you got it.
I have just a question for understanding, because I'm not. The thing is with when you call it forward function, so you started a point like that, like starting point, and then what, like the neural network, what step ahead will it calculate? All the steps ahead, like from or only the next step. So you start with x0, and then if you push the forward, is it gonna calculate then the next value, or then when, like, the thing is, for me, it's like just for an understanding, how much forward does it go into, and then when do you?
So let's say from x0 to x1, let's say x1 is the observation net, x1 is the solid state solution, or the
Okay.
at time one.
Mhm.
From x0 to x1, we use a numerical solver,
Mhm.
which takes certain steps. We don't know how many, and then it gives us x1.
Yeah.
So it's not one step. I mean, if you consider computational graph, we don't know how many steps.
Okay.
But then this one, like now we obtain x1, right?
Yeah.
Typically, we would like to compute the ODE solutions, like for, let's say, up to, like, let's say, time 15,
Yeah.
and like at 1,000 different points.
Yeah.
Then we need to move from x1 to x2 and
Yes.
x2 to x3 all the way to x
Yes.
1,000.
Yes. And what does the neural network calculate then? And like the force, that's for me not clear. Like if you call it force, is it gonna be, because I mean you have to.
So okay, let's go here. All the way up. Yeah. So let's say this is x1, this is x2, right?
Yeah.
Again, this is x2,
Yeah.
this is x1, and that's a neural network.
Hmm.
So basically x2 is equal to x1 plus some constant times f of x1. So neural net output at x1.
Okay. Network will then output the F4. But basically,
Exactly. Yes.
Okay. And then when does the integrate, like this numerical solver come in? Like after you've done a lot of steps, like do you do the 10 steps now?
That's exactly how the numerical solver works.
Okay.
That's what it is.
Okay.
But
Okay.
delta t is not specified. Like delta t numerical solver chooses.
Okay. Okay. Thanks.
Yeah.
Oh, I just want to make sure I understand him correctly. So what we are doing here is first we have initial value.
Yeah.
And we will select some time points to
Yes.
evaluate this thing.
Yes.
So and we can calculate all this xj, and then we'll train the neural network by minimizing this.
That's right.
And then like so how do we choose the this
I mean,
time range here?
These are typically given. Like
Okay.
you have some data set of yn, right?
Mhm.
And like one would typically say, I have like exactly like this observation came at this point, that came at that point.
Okay,
These
so
are correct.
this one is fixed, but this
Yeah.
one is like we just randomly choose some value.
I mean, we use the one in the data set, like we use y0 as the initial value, which we like.
Why would you use y0? Because there are some noise.
Just
right?
what I do is completely wrong.
Okay.
You got the point, but I mean, this is more like simpler, like easier to communicate. That's the only reason. But it
Okay,
is
I
wrong.
see.
We will just learn it. We are gonna learn it. Like,
We can also learn x0.
of course.
Oh, okay, cool. That's interesting.
Yeah.
Thanks.
Yeah.
So, for me, it feels like a little bit like a regression task. It feels like you're trying to do this regression task on time.
In time, like this is like a time series regression, we could say.
Yeah, it's like a time series.
I mean, like a mean squared error regression.
Yeah, it feels like if you change this app into a y equal to f given x and t, does it do the same thing? No.
Now it would be like for this you would need to know xn, right?
Yeah.
But here xn is completely unknown. We only know the initial value x0, and xn actually comes from the ODE system. Like we integrate, and then the result is xn.
Uh-huh.
Otherwise, it would be just like imagine like 1D regression, where you have a bunch of it would be that case. But here xn we don't know. We compute it.
But the training data, you know the time steps and
Only the time steps,
Only
and
the
the
steps.
observations.
And
Like
observations.
someone says that like I observed this at this point, like observed that at that point, and that. Okay. Now this is gonna be the setup, and I have again one picture stolen from a neural ODE paper. So what is happening here is that like so here like we have a lot of unknowns. Basically everything is unknown. The initial value is unknown. The dynamics are unknown. The ODE the BAE mapping is unknown. Like nothing is known. And like a nice picture that would summarize everything would be like we have a bunch of observations. Say we have an RNN encoder that would give us some it's like amortized inference, right? There's an encoder which would give us some initial value distribution, let's say a Gaussian. which would give us some initial value. And then we learn an ODE system here. By the way, this is the latent space, like upstairs is latent space and downstairs is data space. We would solve an ODE system, and then there's a mapping. This is the decoder part now. So this is kind of the setup. Yes. So again, with this time we will try to be more Bayesian. So we'll do variation inference. And again, we will use, like, what we need to define is one initial value distribution, right? So this guy over here. And this will be simply like some encoder, some deep net, whatever you want to use, that would only give us an initial value. And then again, we will learn the latent dynamics by a neural net. But now we'll go fancy. We will use a Bayesian neural net, or we will just define a prior, or like we will perform approximate inference on the neural net weights, so that we can, have some uncertain quantification, right? And then we will also learn a decoder. So this thing over here is going to be our approximate posterior, right? So again, like an inference network, what was it? Like encoder, like amortized inference, right? Which would eat the sequence and then give us some initial value, whatever it is, and then mean field inference for the neural net weights. Now, one super funny thing is that once you have Bayesian neural nets are stochastic, right? Like you would basically have one, like if you perform mean field inference with DNNs, then you would obtain one approximate posterior on the weights. So how you compute the neural net output is typically you sample from your approximate posterior, you give your input to the sampled weights, and then it would give you an output. Now, if you have like a different set of weights, then the output would be different. So like for the same input, different sets of weights would give different outputs, which is completely fine. But now, if you look at the definition of ordinary differential equations, this is completely incorrect. So for a system to be like a valid ODE system, like the differential function should be continuous. So like whenever you evaluate the differential function twice, it should give you like the same output. This is why our framework will be a bit tricky. What we're going to do is we will define our approximate posterior, right, on the neural net weights. We will sample a bunch of weights, and the sampled weights, they basically define a function, right? And then this function is the one that we will use for integration. So we will always use the same function for integration. Yeah. Now, let's do some derivation. So this is our log likelihood, right, that we'd like to optimize. Well, it's difficult to optimize. We do blah, blah, blah. At the end, we observe, we end up with this algo. And the last two terms are not interesting at all. These are like simple KL divergences, like everything is Gaussian, KLs are like tractable, whatever. And then this thing is super nice. Now, what we have is, this is called expected likelihood, right? This complex term, where the expectation is with respect to whatever posterior that you have. So nothing with ODEs is going on here. This is like standard expected likelihood term. And inside you have the log likelihood of the observations with respect to the variables, like that you had the approximate posterior on. And then again, this might look complicated because like W is like some set of weights, Z0 is some initial latent, and Yn is an image, right? And or it will be an image, but this will be clear. And typically, like almost in all my publications, I use Monte Carlo sampling to approximate such integrals, such difficult expectations. And how you approximate this guy with Monte Carlo is basically you draw like from your approximate posteriors, like you draw an initial value, you draw a set of weights, and then they go in here. And then this is like where the Monte Carlo stuff comes in, right? You just sample, evaluate the log likelihood, and then like compute the mean over your samples. And again, in my own research, L has always been one. One sample is enough. I'm not sure how Bayesian this is, but I mean, yeah. I'll take the questions at the end, all right? Yes, so basically, in our framework, how it works is that we sample from initial value distribution, like here. We sample the set of weights now we have the initial value and the weight samples, right? And these are complete, like these are just enough to solve the ODE system. And then given these two things, initial values and weights or function, we just compute the ODE solutions, like at time t0, t1, whatever, all the way to tn. Again, these are latent. And then we have a VAE mapping that takes the latent ODE solution and gives us the observation, or like something that's going to match the observation, right? It looks like magic, like a lot of things are latent and like sampling is going on, but that works, I promise you. Yes, and a data set that I'm gonna have will look like this. This is called I should run this. This data set is called rotating MNIST, where like I show you 5 sequences, 5 data sequences, and first initial values are all like standard MNIST digits, and then each sequence is of length 16, I believe, and they're simply rotated. And yeah, like we specified everything so far except likelihood, and likelihood of course depends on data, right? Here, like if you have like black and white pixels, then you would typically use Bernoulli observation model, which is well specified like this. So the decoder would take an hidden state, like ODE solution as input, and that would give us the parameters of the observation model, right? So if it was a Gaussian, then it would give us the mean and variance. Now it'll give us just I don't know how to call this. It'll give us some xn that we will compute the likelihood with this Bernoulli model. Okay. Yes. Now let's see some implementation. So this is going to be more fun. So here I define my ODV class where like I have Q. Q defines the dimensionality of the latent space, right? Like we're going to solve a latent, like we have a latent space and the dimensionality of it is completely arbitrary. Like if you are doing VAE for MNIST, then you would say, okay, like my latent states are going to be 10, right? And this is some like parameter that you should choose carefully. And here it'll be something like 8. But yeah, that's the first input. And the second input is like how many filters you are going to have in your convolutional neural net. Now, we have one encoder in our model, right? We have one Bayesian neural net for a differential function. And the inputs to Bayesian neural net are like dimensionality of the ODE system. And the dimensionality of the ODE system is dimensionality of the latent space, right? And then like some like number of hidden layers, whatever. And then there we have the decoder as well. So like we have encoder, BN, and decoder, like VA plus like ODE and VA stuff. And then this defines the observation loss binary cross entropy, right? And then let's see the forward function. This is beautiful. Now, inputs to the forward function are the time points. So time points are, we assume that they are always known. Like someone says, like I saw a straight tree at time 0. I saw like a 30-degree rotation at time 1, and it goes like this. So this is known. And why? The observations, they are also known, of course, right? And now the input sequences are of shape this. So it means we have t time points. In our case, it's 16. There are n trajectories in our mini batch or our data set. And each particular observation is of shape 1 number of channels, right? Black and white. And 28, 28 is a standard MNIST. Now we take the observations there, like this is the observation dimensionality, and then we give the observation to our magic encoder. And then the encoder would give us some mu and some sigma, which are the parameters of the latent initial value distribution, right? We have one like encoder that's supposed to give us some initial value, and like it is what it does. And then, so okay, let me go up a bit. Now this is what's going to be in the forward function, right? So this step, this is like where the encode, the first line is where the encoding happens, right? And then we will need to sample well, actually, we first encode it, then we will need to sample from our initial value distribution and sample from our BNN. And these are quite convenient because what you do is you have like your Bayesian neural net, and then you call the draw f function that would give you one function. And this function, what's nice with that function is that it is fixed. That means like you can evaluate it anytime you want. And like it would give you the same output once you evaluate it twice. So that's nice. And then, I mean, this is a function draw, but not an OD right-hand side, right? Because OD right-hand sides, these are functions with signature, like where the first input is time and the second input is state. It has always been like this. That's why we define like a function, like OD right-hand side here. And then we draw from our approximate posterior, we draw from our encoder, right? Again, like nothing interesting going on. And then we compute the OD system forward, right? The first input is the OD right-hand side function. Again, like inputs are time and state. And then the second input is initial value, like as always. Like that's the function that I've been calling like 10 times since the beginning, right? And time points and some OD solver method, like numerical solver, which would give us some latent trajectory. And then we have an encoder, right? Sorry, we have a decoder that would map the latent points into observation space. And that's it. That's how we define a OD-VA, like a hybrid model. And then here you compute elbow. Like this function returns, the fourth function returns like a bunch of things. Like this initial value distribution, right? That's a latent trajectory. And these are like the reconstructions, you could say. And then there you compute elbow that you can like work on your own. And now this is where the optimization goes on. And again, nothing special is going on here. Like we use 25 sequences in our mini batch, like we do sub-sequencing so that like, sorry. We extract the mini batch where the sequence length is the same. It is like 16. It was 16 in the original data set. It is still 16. But instead of using whole data set of, I don't know, like 1,000 sequences, we just use 25 in each optimization step. But I mean, that's something that we need to counterbalance, right? Like if the data set, if there are like 1K trajectories and if you only use 25, then you should basically multiply certain terms with 40 or like with this thing over here, right? Yeah, let's use Adam. Let's get a mini batch. Let's compute album, and then like let's rescale and then run the optimization forward. Now, again, this is beautiful, but I'm going to show you like on top, I show you the latent trajectories. So like for 5 different input trajectories, each color matches one trajectory, right? The circles are the initial values, and that's like the resulting trajectory, right? So again, the latent space is 8-dimensional, but what I do is I map it through PCA from 8 to 2, and then I show you what the sequences look like. And I mean, again, here everything is randomly initialized, like VA is randomly initialized, BNN is completely random. And yeah, initially it does not make sense at all, right? And okay, like something is going on, or like just started, like all the trajectories, they go into same direction. That's nice. And now that's the predictions or reconstructions that correspond to rotation or like this particular sequence, right? So the model reconstructs this sequence like that, which is not stupid at all, right? Because like the rotations, like if you imagine that, like if you take all the data points and like put each like on top of each other, then you will obtain this guy, right? So for only, I don't know, like 20, 50 iterations, it starts to do like something, like it is learning something now. See, it gets better. Like now, so basically, like the dynamics are identical, right? For each trajectory, like for each input point, what happens is rotation, right? That's why ideally the latent space or like latent trajectories should be somehow like similar, right? And I'll speak just a bit more to show you what's going to happen in the next iteration because it gets like better and better. And You can also see like all the initial values are kind of on the left of the latent space. This is completely wrong, but you see my point, which also makes sense. I mean, not being on the left, but on the same side. Like all the straight trees should be here, and the rotation should go like this way. And of course, rotation is like a cyclic motion, right? And this is not a cycle yet. Okay, this is still super crappy. So I will stop the execution. And well, I already trained again, right? And now, once you properly train the system, this is what the latent trajectories look like. Now, these are all the initial values, right? These are all straight trees, and they should be all like a cluster. They should form a cluster, right? And they do form a cluster. And the latent trajectory looks like a circle. Again, rotations cyclic, right? I mean, ideally, this is supposed to close, like the loops are supposed to close, but I mean, there's PCA here as well, like God knows what's wrong. And see, now this is beautiful, right? Like you could even say for a particular sequence, even the style is there, like the writing style, right? See, and that was like a training fit, and that's what a test, like test predictions look like. I mean, definitely not perfect at all. But yeah. So again, like I still find this really strange. Like everything is latent. There's like this distribution and that distribution, and then it just works. It's how deep learning works, right? Like you do stuff like throw this and that, and then move. It works. I mean, yeah. I hope so far so good. This is when long break is gonna take place. So we'll be separated for 15 minutes. Then let's start at 40 past 10. All right. So I'm here for the questions, just like a couple. Hi.
Just a second. So, I mean, we have now a notebook, like a collab thing that basically have the same stuff of last year. So downloads of the things and uploads here. So it's on the GitHub. If somebody still didn't manage to kind of we can just say it's here, and it's basically notebook, and then it kind of opens all these things that can be. The only problem is that it doesn't. I don't know. For some reason, there are so many images. Or maybe, yeah, these things basically, right? Let's see. And yeah, okay, but that's important, right?
I mean, I don't think so. What was it? ProbAI?
Yeah.
ProbAO.
Probabilistic AI.
Probabilistic.
Yeah, and then 2023.
This is.
Somewhere. Yeah, there. Just click on this one. This should open.
I mean, I'm not gonna click. I'm just gonna like leave it like this. Yeah. And let me zoom in. How do I? Control plus, right? Yeah. And that's like German keyboard. I have no idea where plus is.
Your keyboard just looks German.
No, like Y is here and Z is there. That's German.
You changed them.
No. Like in Germany, like in German keyboards, Y is there.
Yeah. But like the actual layout.
Okay, everybody.
Yeah, but yeah, that's right. So let's make it like this.
And it was very quickly. I had said the quick direct implementation of the ODE and the training loss goes up. Have you ever seen that?
I saw that oftentimes. Yeah, I mean.
So do you have any idea why the training loss would go up? Like the train, like to minimize the MID and then also the training data keeps going up.
I mean, I'm not that bad, but like sometimes strange stuff happens, and typically, at least in my case, they more like the ODEs forward. I mean, like once I change from Doppelfight, like an adaptive get forward to earlier, things typically start working. I mean, yeah, like Doppelfight. I mean, yeah. Okay, these are like things that I have.
Okay, sorry. Okay, yes, just want to.
Yeah. All right.
So, like you've seen this before.
It's not as bad, but I mean, like it typically goes down quite fast at first,
I mean,
then like it goes up. Okay, this create like that type of creative stuff always okay. Just like use Euler solver. I mean, just at least try. But I mean that I saw so many times. Like, yeah, once I solved this, my PhD was done. Like yeah, these are like super unstable stuff like the ODE folder. Yeah.
Great lecture, really good. So I was wondering about the latent space encoding. It's basically it's learning a representation of all the time steps in latent space, like the RNN encoding.
So no, sorry. What the RNA encoder or here like we have the CNN encoder.
If you go to the slides, like the picture of like figure 1 of the new ODE paper, I think, like the concept figure.
This one?
Yeah, this one, yeah. So the green nets, so the green latent space, we have one for each time step, right?
There's
T0
only
to,
one encoder that eats the whole sequence, and then that gives us one initial value.
Yeah, that's what I'm wondering. So I'm wondering why on the figure it looks like we have this the hidden state for every time step, but then we only learn Z0.
I see. So this is an RNN encoder, right?
Yeah.
That takes a sequence as input. And the way that RNN works is that like it has one, like it generates one hidden state for each observation.
Yeah.
This is like how RNNs work in general. And in this illustration, they show like, okay, this is where is my cursor? Okay, they say like, this is now the hidden state that corresponds to this guy. That's the hidden state. And then at the end, we obtain like, let's say one hidden state, which becomes initial value distribution.
But the zero, the ZT0, it corresponds to like the HT0, or
it corresponds to HTM plus 1 or like N plus 1. Like you completely discard all these guys except the last one, and the last one becomes your ZT0, or like you also transform it maybe.
But wait. But then again, ZT0 corresponds to T0 in data space. So how is it?
No, not in data space.
Okay.
It is in the latent space. So again, like upstairs is like latent space.
Yeah. But every latent space corresponds to the. So ZT0 corresponds to
one of those.
T0 in data space.
Yes. Yeah. It maps. Yeah. There's a decoder mapping.
Like that. I found it confusing that I take HTN plus 1 as my prediction for Z.
I mean, you think it's not the prediction, but then you also map that. There's, let's say, one more function that takes HTN, and then that gives you ZT0.
Okay. So I try to encode the whole latent sequence into the T0.
Whole sequence into a latent initial value.
Yeah,
that's
nice. And then, okay, that's my first question. Second one, so the whole framework is really beautiful because now we have a data space and we can look at the trajectories. But could we, in principle, also solve the MNIST rotation without this fancy data space presentation?
You don't have to do it, but like we do it.
Okay.
Why?
Because you can.
Because I can. Yeah. I mean, but also like the underlying, like the data is. The underlying dynamics are actually in continuous time. That means like the rotation isn't like you can consider. You should. So the rotations are defined in terms of ODEs. That's why an ODE model would match from a conceptual point of view. It matches nicely. From a practical point of view, like nothing changed.
Yeah.
Like you could just use like some others, like any technique that you want that will give you almost the same or even better results. I mean, this is like a natural match.
Cool. Thanks.
I had a more like a basic question. I think probably you mentioned it, but I was wondering like why we're sampling the weights from a distribution when the output of a differential is a constant, or should be a constant.
You mean
every time?
Can you repeat?
So yeah, I was wondering why we're doing variation inference, like why we're sampling from the weights from a distribution when the output should be a constant of a differential, no matter.
Why should it be constant?
Well, in any physical scenario,
I see. Like the differential function is actually fixed,
Yes.
but now you're using like this is again like a more like a conceptual explanation. But like if you are doing Bayesian stats, then what you do is like oftentimes what is unknown is like one thing, but you don't know so much about it, right? That's why you would like to have some uncertainty, like quantification over the unknown thing, like a single thing that you don't know, that you'd like to quantify, like how much you don't know, right? And this is done through like this approximate posterior. So approximate posterior is supposed to tell us like it could be super stochastic, it could be super noisy. That means like I don't know this function. Like I tried to estimate, but I failed. It's like this would be the like what BNN would tell us. That's why like we hope that it would tell us like how good the fit is, or like how uncertain, you know, like the model is.
But we're adding with every weight, we're adding uncertainty. So wouldn't that like add up?
Unfortunately, yes. The Bayesian neural net literature is completely like crappy. And this is like the approximation that we had here, which is like a mean field approximation on the weights, doesn't make sense at all, but it's quite convenient.
Okay.
That's why I mean that should be a BNN lecture tomorrow, which will be given by like a super nice guy. And like there, I'm sure like he will elaborate a lot like on this.
Because I'm just wondering how for MNIST this works, but I'm wondering if it's for more complex systems, it would be completely like, I don't know.
You're right. Yeah, you're right. I mean, using like we as machine learning people should invent more reasonable BNN graphs.
Okay.
In practice, it is in the simple example of
It works.
workish. Yeah.
Other things?
Yeah, I had a similar question. I missed the motivation of the BNN. What happens if we use just NN?
Then you would obtain basically a point estimate. If
Okay.
you are happy, just do it. If not,
Okay.
I mean, yeah.
Okay. So
It's like encoders versus autoencoders. Do you want to have like some uncertain quantification, which is typically super crappy?
yeah.
And like what happens usually here is that we have a mean field inference for the weights, right? And then like you check the how uncertain are we, like how uncertain the variation posterior is, and typically it is like super sure, like the uncertainty is super narrow. Like let's say the variance is something like 1e minus 4. So like practically there is no practically it's a point estimate.
Okay. Now I see. To add some regularization on the latent space.
Exactly.
But then, like, why on the weights? Like, why not on the Z directly? Like on the
You also have an uncertainty.
activation. Like directly.
You mean on the trajectory?
Yes. Like I think with BNNs also some people do that, right? Instead of weights, they put priors on the
function output, right?
yes,
Yeah,
or the
that's right.
yeah.
Now,
Then it will be on Z, maybe,
now
but integrated.
I see your point, but now look at that end, like look
Yeah.
at the forward simulating equation.
Yeah.
They're like, this is like we use an ODE solver, like, and the inputs are time points, which are, let's say, known, and then initial value and differential function. So like either the uncertainty will be, I mean, not either, but the uncertainty could be on the initial value
Yeah.
or on the unknown function, right? So we do have uncertainty on like both, right? But I mean,
Yeah.
the way that we place the uncertainty on the function is stupid. Like you could also place your uncertainty into function outputs,
Yeah.
which would really complicate the whole inference, which
Okay.
would work, which I tried, which took like several weeks of mine,
Yeah.
and then did not publish at all at the end.
Okay.
But I mean, yes, functional BNNs, where you have the approximate posterior on the output,
Mm.
they are beautiful, but they're super difficult to apply at least here.
Okay. Yeah. Thanks.
I completely missed who came first.
Yeah, like I was. Yeah, I would just like a very simple check that I understood the concept correctly. So is it always so? Like in this case, it seems to be so that the latent space is like the vector field, like somehow represents the true vector field. But is it always so? Like you could, in principle, you don't. There's no way to kind of force it. Like does it just like the way that we have set up this problem that it somehow reflects the true vector field, or
I mean,
have I completely misunderstood that somehow the latent, like what is the interpretation of the latent space? I guess my question.
Yeah, the problem is that there is no interpretation of
Yeah.
the latent space. Like when you look at an 8-dimensional, even looking is difficult. Looking at an 8-dimensional object is difficult, right?
Yeah.
And what happens at the end is that when you map, or like, how should I say this? So like the sanity check or like the checks that we do is either like we try to identify the latent trajectories,
Yes.
or like the reconstructions, like if the predictions are beautiful and whatever. And these are not direct ways of checking how the vector field is, but I mean, at the end, we could at least say we learned some vector field.
Yes.
That would give us meaningful stuff. But what this vector field is,
it's like somewhere in the
it's
somewhere in the machine, but we cannot take a slice and okay, here it is.
Exactly. I mean,
this is what the machine thinks that the vector field is.
Like you can maybe make it into 2D.
Yeah.
But I don't think it would be beautiful or like.
Yeah. I get it.
Yeah.
Thanks.
We have more conceptual questions. So first of all, I'm wondering the application thing, the applicability. What let's say how really this can be applicable to solve problems which can be complex.
I mean,
let's say, I understand that with the 28 on 20 pixels it can work, but let's say if we take a higher resolution or even three-dimensional images, would that make sense? Like, and what is the computational cost? Is it heavy or like?
I mean, I would say for a three-dimensional problem, using this thing like a latent ODE thing wouldn't make much sense. Like we already defined it in like a data space ODE right there, like you could just use it. But I mean, typically, ideally, we have really like few assumptions here. Like the only, maybe you couldn't say the only assumption that we have is the system should be in continuous time. That's
but so, like I said, the images are not in continuous.
Not the images, but the dynamics are. Like you look at the problem and you say that okay, like how the thing evolves over time is continuous. Like it's not playing.
That makes sense.
I mean, like for instance, we applied like similar tools to reinforcement learning.
So this in general could be a good application for the change from point A to point B in time.
Exactly. Like whenever something changes over time, and like in this way, in like a kind of auto-regressive way.
Yeah. So can I be more specific? Let's say if you want to observe tumor change. So this technique could be applied because it gives you a possibility.
I mean, I even had like one application where like certain measurements are taken from like some patient or like many patients, and then like sometimes people are given drugs, and then certain measurements they like suddenly go down, and then like once the drug like effect is gone, they go up, right? All of these are happening in continuous time. That's why like I tried this thing, but there's like certain external control, which are like when drugs are given, right? So I showed the external control stuff at the very beginning, and like this is like a super like a nice match between this type of data and
because it seems like that it gives how to say it defines the function. It sounds like this is a cool stuff because it seems like things should work in that way. We shouldn't do everything by hands anymore. Like it doesn't make too much sense. So like it's Is there a possibility to contact you if I would have some questions?
Like,
because your name is anyway on the list.
I mean, you should find my email through like ProbAI website.
Yeah, or maybe you use LinkedIn or whatever.
I have one LinkedIn account that I check once a year.
Okay. So email is a better option. Okay, thank you for your insights. Sure.
I've got a question about so your implementation of a Bayesian neural network, right? So you sample the weights and then you just basically you initialize a new network, essentially a neural network where you just basically do the matrix multiplication, the activation, right? And then draw that F. But then it's an Bayesian framework, right? The idea is that we want to learn a posterior over parameters, right? So the data is given the data.
Yeah.
But are you learning it? No, right? Or
I am learning it.
I'm like,
this is now my posterior.
Yeah.
It is stupid. It looks stupid, but this is like how mean field inference is done.
Yeah. But then the priors of your network, are they just Gaussian?
I mean, they are like simple Gaussians, which doesn't make sense at all, right?
Yeah,
why should have a weight, like Gaussian prior?
Yeah, that was
because some people did it, and it's convenient. It's completely stupid.
Yeah.
That I understand, but
But did you try other things or?
I mean, I tried. I was just answering a similar question, but this is super convenient in terms of computation. and like BNNs are not yet super well established.
No,
That
no.
means like this is like the most convenient and most commonly used inference for BNNs.
Yeah.
Like mean to be again, completely stupid, but works in practice.
Yeah, no, the reason I asked because I was thinking is it's in, it's for any of these kind of systems, you can assume that, let's say, you assume a given dynamic that it should follow. Let's say, so you can think that you can assume that you know the vector field, but you don't
For
know,
instance, like
have a
place
distribution over the vector field, like, or the, let's say, so the dynamics that you want to have, and then you
could even say like I want like a vector field which is like that smooth or like which is not smooth at
that's
all.
what I'm kind of looking
These will
into.
make perfect sense. Yeah.
Yeah, in a okay, yeah, thanks.
Okay. Yeah, like I should start. Yeah. Oh, no, you're not gonna ask either.
I can come back.
Okay. Yeah.
Are they catered 3C? Sorry, they go actually because you have like
Input to what?
you have the plot, you have model.
Yeah.
Model, so you have 2 lines, 3 being rotated.
Like each line is one sequence.
Yeah, you have one which is coming from one is training data and one or test data, one is from the model.
Show me which ones. These ones.
There, yeah.
So that's the training sequence. The first one, the second one is model predictions.
But are all those 5 going into your model, or is this the first one going into the model?
Like this one goes into and that one comes out, and then like this one also goes in and that comes out.
It's further to the right. Or left.
Like the whole sequence goes into the model. Like the whole 5 or like 16 images.
Okay. At
What is
prediction time as well.
That's right. Yeah, that's right. But like you could build your model so that it takes only the first 3 frames as input, and then it gives you like 50 states, 50 operations.
What's happening here?
Well, actually here only the first image goes in, and like the whole sequence comes up because like the first image is enough compress all the information, right? But I mean, in general, it could be like the whole sequence, it could be the first point, and like however you wish.
Sample. But do you resample after each time you've trained them?
Exactly.
Okay.
In each training iteration, I sample, but I mean, the number of samples that I use is one.
Sure, but like it is resamples. Yes. Right. Thank you.
Yes. I should really continue. Can I ask your questions later?
Okay.
I'm sorry, but yeah. I think it's already over 40, right? So let's continue. Like I had really nice questions, which I had even sometimes difficulty answering. And you could say, like, I had multiple questions about the BNN stuff, Bayesian neural net. Yes, the posterior doesn't make sense at all. Like the price that I have makes no sense. I mean, the whole BNN literature is a bit, I mean, there's room for improvement. And tomorrow there will be, I'm pretty sure, like an amazing talk where you should address the same questions, because I do know that he has like Lovato has like better answers than I. But I mean, yes, we use DNS so that like the dynamics are unknown, right? And we would like to know, we would like to quantify our answer. And that's why we use a DNN. And yeah, that's like one way of doing it. So you could, by the way, like in principle, place a GP. So the dynamics could be defined in terms of a GP. And that I'll talk about like at the end of the presentation. And like there you would have more beautiful answer of quantification. Please continue. I should also do this thing here. Now, so far, we've been talking about mostly time series applications like sequence learning. Now we will completely change our direction from sequence learning to classification. And this is basically where the neural ODE idea came from, or at least this is like the first thing that neural ODE people show in their paper. So the idea is that, or like the connection is that, okay, maybe one disclaimer first. I'm not an expert in deep stuff at all. Like I don't know much about deep learning, and like not about classification, not about like these VGG stuff like ResNet. But there's one thing that I know, which is that residual neural networks, they are one of the first successful applications of very deep nets. And by very deep, I mean like a ResNet could have like 150 layers, a gigantic computational tree, and it still works. And so okay, ResNet is defined in terms of what is called a skip connection. And here I have like a typical hidden update equation of a ResNet, which goes like the hidden activations at layer n+1 is equal to activations at layer n, previous layer, plus f of xn. So f is a neural network. So from like hidden layer n to hidden layer n+1, you have a neural network in between, but also you have the skip connection. So the next activation is the previous activation plus f plus neural net. Now, if you compare this equation against that one, the second one, and the second one is like this is how we defined our ODEs, right? If delta t goes to 0, that's a valid ODE system. And now, like these equations are identical, almost identical, up to this like constant thing here, and plus here, like for each layer in a ResNet, you would have like a different set of parameters. Here in our ODE system, we had one like single set of parameters, but then the differential function would also take time as it, right? That means like there is some like these are almost equal, you could say. Yeah, so basically like people looked at that and they said that, well, ResNets are nothing but ODEs, come on. And then they were like, I mean, if that's an ODE system, and if ResNet isn't just an approximation of an ODE system, like you could say this equation, and like these are identical up to this guy over here. And then they asked the question, like, why do we solve an approximate ODE system? But instead, let's use the second equation here, and let's do the integration properly. Like, why is delta t 1? Let's use a proper ODE solver that basically gives us like a proper trajectory. And now that's like the analogy. Like here on the left, you have ResNet. You have like 5 layers. That's the input layer. The last one is the output layer, and like 4 hidden layers. And here I get 7 different inputs. Like this is the first input, and like the trajectory goes like this, or like the activation go like that. And then on the right, you have the ODE network. This is not in continuous time. This is an ODE system. Like here, each input is evaluated 5 times, or like 6 times, whatever, because there are 6 layers, right? But on the right, this particular guy is like evaluated 4 times, right? And that one is, I don't know, like 10 times. This one is like 15 times. Why is that? Because you don't know how the ODE solver works. Like it could evaluate the system as many times as required. And yeah, so that's the idea. Like let's completely forget about ResNets and let's just use ODEs. And what happens at the end is that, of course, if you have a deep model, if you have like enough parameters, if you regularize nicely, you would always obtain state of the art. Like this is, I know, probabilistic AI summer school, but that's the truth. And this is why the results are not impressive at all. I mean, kind of equal, you could say. But I mean, I hope that you get some conceptual understanding of like what is what. Yeah. So let's do classification. Our data set will be standard like empty stack data, where we will have a bunch of images xn and corresponding class labels yn. And then our framework, it consists of 3 different like procedures. The first one is downsampling. That means we take an image as input, and then we extract some relevant features, like features that are relevant to classification, right? And then we had the second step where we take the output of the first block, like we get the relevant features, and then we transform it. And how to transform is you either use a ResNet or you use an ODE. And again, ODE is the ODE system present. And then the output of the second block would go into the last block, which is just a bunch of fully connected layers, which would give us, like, let's say, class labels or like some prediction about class labels. So again, this is our optimization objective, where we have a cross-entropy loss that goes over each, like all data items, where yn is the true class label and y hat n is our prediction, and y hat n is equal to this thing where we first downsample, then we transform, then fully connected layers. Okay. And now let's see what a ResNet implementation looks like. By the way, maybe one announcement that I should have made already. now on the GitHub page of like ProbAI, like this summer school, there's a link to a notebook which I believe opens in Colab, so you could also check out the web page. But yeah, now this is our ResNet implementation, and like what happens here is that we specify a number of blocks and like certain parameters of each block, and then all we do is we create a bunch of ResNet blocks. So here we create as many num blocks as input, as many ResNet blocks as num blocks, right? And this is like how we specify a ResNet. Now let's look at like what is inside the ResNet block. So we have like one, you could say, transformation layer. This is like some neural net, like some magical thing. And what it does is it takes some normalization, some like nonlinear layer, some convolution, like repeat the thing, same thing. I have no idea why they build it this way, but it works. I mean, that's deep learning, right? And the forward function is basically where we compute like the output of this particular ResNet layer, particular ResNet block. And what it does is it takes like one input, it saves the input into this shortcut variable, and it computes the neural net output, and then sums them up. Okay, so now this is like basically the last line is where the skip connection is implemented. And this was like a huge advance in deep learning, this summation. Yeah. Okay, so that's all about ResNet. And then let's see our neural node implementation. Now again, this will be very similar to what we had. So inside the constructor, we again have like a bunch of, like previously inside the constructor, we had one multi-layer perceptron, right? Which we used to learn like a sequential data. And here inside the constructor, we again have the differential function or like related things, but this time these are like the magical group norm and redo and whatever. Or maybe like one of the things inside the constructor is concat con2d, which I will talk about like right after. And then again, we have the OD right-hand side function, as always, right? So it takes time and state as input. Again, these are signatures that, well, torch defect library wants. And then what it does is it does some normalization, some redo thing. And then here we have the convolution layer. Now, inside the convolution layer, we have like both time and like out as input. So that means now this is our differential function, right? Or the right-hand side. Now it is a function of time as well. The first time in its presentation, time is an explicit input to differential function now, right? And yes, and here we have a forward function, which again computes the OD system, runs this guy, right? And the inputs are always the same, like differential function, like the input initial value, and now integration time points. Now this is a bit tricky because previously we assumed that we had some observation, like a sequence observation, right? And someone told us that like we observed like this particular data point at this time and that particular data point at that time. So we knew the observation times. But now we are doing classification and there is no observation time, no concept at all. And we need to integrate the system some way, right? So what we do is we say, okay, I will integrate from time 0 to time 1. Why? Well, you can see that like you can say like a hyperparameter of your model, like how many ResNet blocks do you have? You just choose it by cross validation, right? And then here you just say, I integrate the system from time 0 to time 1. Could be from 0 to 10, I don't know. But I mean here, the shorter, the faster, right? And yeah, one thing that I haven't told you about this is the concat con2d. Again, nothing special is going on. This is actually a 2D convolution, right? So like we will work on images, like again, like images. That's why we need to have convolutional layers, but we would like to parameterize our convolutions with time as well. So now this forward function takes both time and state as input. So it repeats time, like as many times as required. It concatenates time and state, and then like the output goes into the, or like the concatenated like thing goes into the layer. This is like how you can define a convolution that would also change over time. So if you give the same x at 2 different times, our convolution layer would output 2 different things, like a time varying CNN. Time, yeah, you could say it that way. Yes. I think I should have run this and that one as well. Yeah. Okay. Now see the training. So okay, either we use an ODE net or ResNet. So this could be just ResNet. And there we have like number of filters. This is like how big your network, your CNN is going to be, right? We have downsampling layers, again, like some convolution, normalization, whatever. And then transforming, this is like the first layer that we had, right? And the second layer is feature transformation layer, which could be a neural ODE or which could be a ResNet. And then we finally have the fully connected layers where, again, like some normalization, redo, whatever. And then at the end, it outputs a 10-dimensional thing. So we will do, I think, MNIST classification, and there are 10 class labels, right? And the output, the final output of the whole classification algorithm will be a 10-dimensional vector where each element corresponds to like models belief of like the image belonging to this class. Yes. Then we basically learned. That's the learning rate that we have. Number of optimization iterations, like batch size, simple stuff. We load the training data. We use SGD for some reason, cross entropy loss, and then, well, we just run the training. Again, the model, it would take X as input, like takes an image as input and outputs the logits, and then this should be cross entropy loss. Anyhow, okay, the loss does not drop yet, but if you like run that enough, it will go down. Now, one thing which I kind of like hide from you is that now this is the line where I perform forward integration. This is like where we compute the ODE solution from time series. Now we have been using an ODE solver called Docify. This is called an adaptive step solver. So now I'll go into a bit to the numerical solvers, but these are not super important. But maybe you may want to study in the break. So like an adaptive step solver would work so that, again, like when we use a numerical solver, we perform certain approximation, right? And ideally, we would like to be as accurate as possible. So we want our ODE solutions to be as close to the true solutions as possible. But that means like if your delta t goes to 0, in the limit, if you remember the equation, like if you remember this equation now, in the limit this holds, right? So the smaller delta t, the better. But I mean, if it is too small, then it would take forever to compute the ODE solutions, right? So there's certain trade-off. And adaptive step solvers, there are like 2 sets of solvers. One is called like fixed step where delta t is fixed, and the second one is adaptive step solver where delta t changes like over time. And you could basically say to a numerical solver that like I can live with like this much error. Like I don't care if the ODE system is like super accurate or not, just like return me some outputs, but please don't exceed this much error. So you could say that. And you say this in like via these 2 parameters. So these are called tolerance parameters, relative and absolute tolerance. So you don't want to make like this much mistake relatively to something and that much mistake absolutely. So the smaller these 2 values, the longer the execution would take, but the more accurate the solutions would. And why are these numbers there? Because like I guess it was already there. I'm not sure. I just put it. In practice, like one should choose these really carefully. Like one needs to make sure that this thing is like your ODE system is computed as accurately as it should be computed. Right. So now we will have again short break. You could maybe look into like the code a bit. You could try like different values. Like I won't suggest like changing number of filters because it doesn't make sense at all to me at least. But I mean, you can play around with like the integration time. You could, for instance, like check what happens if t is not there, like if you don't use t at all. Or you could, I guess I put, okay, now the loss goes down and the training, like accuracy is pretty good, right? Or you could just check this link where these like tolerance parameters are explained more in detail. And one last thing, which I should have said already. Now, in this framework, what happens is that we solve an ODE system, right, from time 0 to time 1, and we only take the last state solution. Like there could be as many state solutions as we specify, right? But we are not interested in the intermediate guys. So in time series data, we fit each and every like time point, like each and every ODE solution to one data point, right? But this time it's not what we do. This time we just take the last guy and then like give it to some like fully connected layer, because this is how the pipeline is. Yes. So again, I will stop for 5 minutes. We can come over for the questions and then we'll continue. So let's continue. This will be the last application of neural ODEs. By the way, again, like one thing that I forgot to say is that so in the original neural ODE paper, they discussed 3 like use cases for neural ODEs, which are classification, normalizing flows, and time series fitting. And now it is time to look at normalizing flows. I hope you are still with me. And luckily, yesterday, Didrik covered normalizing flows pretty well. That means I could skip most of the stuff here, or maybe all stuff there. And in continuous time normalizing flows, like the idea will be, like in normalizing flow, what we do is we take one random variable from some base distribution, right? Like here, that 0 is the, you could say like an initial random variable that follows, let's say, standard quotient. And then you take this particle and then you like transform it. And then at the end you obtain like a more, like another particle that follows a more complex distribution. Like that's the whole thing with normalizing flows, right? And now here we have a bunch of discrete transformations, right? You have, let's say, K transformations. This is pretty much like having a resonance with K layers. And again, the idea comes from like the continuous time normalizing flows idea come from like the same observation, which is that like, why don't we replace these layers, discrete transformations, with an ODE? Like, why would you want to do it is, I mean, it is interesting because, well, what would happen at the end is a like nice research question, I would say. And in practice, it has like certain benefits. Like if you, okay, maybe this will come later. So okay, that's the whole idea with continuous time normalized flows. You start with a base distribution, like a simple one, like a Gaussian. And now you have one ODE mapping. Again, starts from time 0, goes to all the way to time 1. And then you have this vector field. This is like how the particles or like how random variables should change. And at the end, you end up with this distribution, which is, you know, multimodal and super complicated. And like you could generate images or like whatever. And again, if we had a normalizing flow, then we would see like bunch of, let's say, like discrete layers and discrete transformations. Whereas here the transformation is like continuous, like the arrow is continuous. There is no jump, right? And okay, maybe now I could tell you this. Like here we had this nice, beautiful change of variables formula, right? Which was actually defined for transformations like that. I mean, this is not what we do in continuous time, right? In continuous time, we compute ODE solutions. We don't do such transformations. So this rule, change of variables formula, it no longer applies. Luckily, neural ODE people, they invented this thing called, I mean, I'm not sure if they invented, but I mean, in the paper, they include this thing called instantaneous change of variables formula, which basically says, if there's a particle that follows this ODE flow, like basically this I'm going to refer to as like an ODE flow because well, it's a flow and it's an ODE. And if a particle follows an ODE flow, then the log density, which is the upstairs, right? it also follows a differential equation. So that means the change in density, in log density, is given by another ODE system. Now, if you remember, like we have a particle that follows an ODE. The gradients, they follow ODE, right? Now the log density change, it also follows an ODE, like a whole complete framework. And now it has this nice convenient form where, again, df, okay, maybe let's look at the second equation, which says the change in the log density of the final particle, like ZT1, is equal to log density of the initial particle, which is like the Bayes distribution, right? And then we compute this integral, and inside we have a trace, and we have df, which is the output of the differential function, differentiated with respect to dz. So again, z goes through this transformation, and then the log density follows this guy here. And of course, now this f and that f, they are identical. That's the same thing. Now, strange enough, there are two integrals, right? And what you can do is, well, you can compute them in parallel. You just solve an ODE system where the differential function is a concatenation of this thing, whole thing, plus this thing. So the code will be, I think, like the code will make things more concrete. But let's first implement the trace operator, which I think I could quickly do thanks to Diederik. So, like in trace, we are interested in the diagonal, right? And the diagonal of what? Diagonal of this Jacobian, right? So what we do is we have a for loop that goes over the dimensions, like for a d-dimensional system, if the Bayes distribution is d-dimensional, this for loop iterates d times. And then we take the ith output, function output, right? We compute the partial derivative, or like derivative you could say, with z, and then we take the ith output. So this corresponds to like ith A3 of the Jacobian matrix, right? Trust me, this is correct. And here we have this thing called create graph. Now, if you're not super familiar with Python, PyTorch, this could be a bit confusing, but basically what this says is that, so we are telling the AutoDiff framework that now I do an operation, and then I do a differentiation operation, and this will be a part of my computational tree. That means, like when we do autograph, the whole thing, whatever we compute here, will be backprop as well, which is a bit strange, you know. But yeah, now let's see what the implementation looks like. So okay, let's take one step back. So far, what we did was we did sequential modeling with a differential function, which was a multi-layer perceptron, right? Then we took one step forward. We did what ResNets, where the differential function was like a series of layers like value and group norm and like convolution, right? So in practice, any neural net could be the input, could be the differential function, and this time it'll be what people call a hypernet. So, like, I did not hear about hypernets before, and this is not like, this is why you shouldn't trust me a lot. But what a hypernet does is that now this implementation will be a hypernet, and the final output will be this guy over here. And how it works is that it first takes time as input, and then it outputs UT, WT, and BT. So like it only looks at time and then returns us certain matrices, and then we take those matrices and then compute this operation. Now the state is there. That's the first time that state, went into the differential function, and H is some like nonlinear function. So this is a linear transformation, nonlinear layer, and then another matrix multiplication. And again, all the parameters like UT, WT, and BT, they come from our network. So like F is a magical thing that takes time as input and that gives you like all those matrices. But in practice, you could even put like a convolutional net there. Why not? You could put a multi-layer perceptron, like a BNN, Bayesian continuous time normalizing function, right? And here they chose this one. But that works, not the other ones. I tried multiple perceptron as well. Now let's see what the implementation looks like. I will first show you the forward function. This is where we do integration, right, as always. And the first argument is the OD right-hand side function, which I will detail next. But now we have two initial values. Again, what we do is we compute two OD systems in parallel, right, which are these guys over here. That's why we need two initial values. That's why we need like Z, T0, and like corresponding log density. So again, these are inputs, like inputs to the forward function. And then we use again Doppify, and then we forward integrate. Now let's look at the differential function. Again, as always, it takes time and state, like state as input, but this time our state is a like a pair, right? And the first guy corresponds to the particles, and the second one corresponds to their log densities. Yes, their log density. And what we do is we enable the gradient computation because we will need to compute Jacobian, right? That's why the gradient should be enabled. And then we said that we will backprop, we'll compute like a gradient with respect to this guy. So please, like, I will need the gradient. So please, like, keep that. And then we first compute the differential function. Like this particular line was like what we had in sequence learned in like the second section, right? And then on top of that, what we do is we take this output and it becomes the input to the trace function, if you remember. We compute the trace, which is like what we implemented previously. And then it gives us log, like a derivative of log density change. And then we return a tuple again. That's it. I mean, well, that's the implementation. Yeah. And for training, that's going to be the target data set. So we will learn a flow, continuous time flow, that will start from a base distribution, which will be like a Gaussian, right? And then it will continuously transform the particles from the base distribution. And then we will end up with what is called a two-circle distribution. So these are two discrete, two discrete circles. And what I show here are like a bunch of samples from the from the target distribution. And yesterday Diederik had similar figures, but there were like spirals, right, instead of like two circles, and like the colors were nicer. But I mean, that's the target density. And okay, what we do is we define like all the parameters. So again, these are the parameters of our hypernet, our differential function. These are very much like how many layers you want to have, how wide the layers are going to be. And these are the integration time points. So we run our continuous time normalizing flow from time 0 to time 1. Why? Because we chose that thing. And some other parameters related to optimization. And then we create the normalizing flow there. Now, that's the interesting bit. Now, so far, we always started integrating from time 0 all the way to time 10, right? And this time, it will be different. We will start from time 1. We'll go back to time 0. And why? Because yesterday, we saw that the way that we learn flows is that we take samples from the target distribution, and then you like use the inverse of the transformation, right? Like you do it, and then you end up with the base distribution. Now, we are not going to do any inversion at all because all these systems are like nicely invertible. That means you just, instead of integrating from 0 to 1, you integrate in the other direction from 1 to 0. And it automatically, like, if this is the forward direction, like it automatically goes into that direction because, well, I mean, that will be much easier to explain. So we will start from there and then integrate from 1 to 0, and then we will match this density, right? Isn't that beautiful? Like, okay, the trace implementation is tricky, I know, but I mean, you don't have to do like, okay, take this like long vector, like cut it into two. These guys will be transformed like all the way up, and the transformation here will be a function of this and that. You don't have to think any of these. Like no determinants, no matrix inversion, nothing. You just need to implement trace carefully, and like I oftentimes in my research try to implement stuff like that, or like stuff like this. And I mean, at least for me, if you forget things like that, like it could easily take a week. That's why I use ready implementations, which I did. Yeah. And now we train. So what we do is, am I be able to, okay. So what happens here is that, well, we train, right? So we take a bunch of particles from our target distribution, like initial density is 0, and then we run our continuous time normalizing flow again in the backward direction. And we are not interested in the intermediate steps, but like only the last guy, like we integrate from 1 to 0, and we take the solution at time 0. So that's like the last guy. And then you compute the base density and like trace term, and that's it. Again, the training is not going well, but it will go well if you are patient. Then, yeah, now that's the beautiful part. Now, what I do here, like you could read the code later, but what I do is I start from this density and like so I start with a bunch of particle samples which are shown by here, and then the corresponding density looks like this. So this is my base distribution. Like once I learn the flow, here what I do is where do I do it? Here. So here what I do is I still run it backward. Hold on, not this one. Okay, this one. So here I create the samples. So this time, again, this is a time grid. This time I go from T0 to T1. So I take samples from my base distribution and then run them forward this time. This way, I end up with samples that follow the target distribution, right? 2 circle stuff. And now let's see how it goes. And record. Yes. So this is gonna be, okay, I'm gonna skip the last break part. So like no break now. I will talk just a bit about related work, like stuff that extend neural ODEs, and then we will have a Q&A session. And if you don't have any questions, we can just go out. I'm not sure if it's lunchtime or not, I don't know, but I mean, feel free to leave after this. So like so far we covered neural ODEs, right? And basically all we did was like we defined some differential function, like put some convolution, like put some multiplier perceptron, and then we took some initial value, like gave them to the ODE solver, and then gave us like some trajectory back. Now that means the state solution, ODE solutions, they depend only on the initial value and the differential function, right? But I mean, if you observe a sequence, let's say, if you like, let's say continuously, if like new data points continuously arrive, then you might want to like update your trajectory or like your predictions based on the coming data, right? Why do we just rely on the initial value if the data keep coming? And like this is what they do in this ODR number. So here the vertical lines, they correspond to observation times. This is now a neural ODE. Okay, this is a standard RNN where like there is no concept of time. This is why the hidden variables, which are shown by color, they are constant. It's a neural ODE where like we just don't care about incoming observations. And now this is called an ODRNN, where we have some continuous time flow, and then we get an observation, we update our hidden state, we update our belief, whatever it is, and then we continue to integrate, and then like new observation, then like some of it goes like this. So like, if you feel like, well, the new observations that I'm gonna have, they will be useful to like whatever I'm doing, then ODRNN would be a better framework, I would say. So this is OD2E. There, like the idea is like most of the physical systems are actually defined in second order dynamics. That means typically instead of only positions, like if you know the position and velocity of a certain object, then like dynamics can be expressed quite easily. Like the time derivative of position is velocity, time derivative of velocity is acceleration, and then you just learn acceleration. That's like the idea of this paper, where this time you have 2 encoders. One is called velocity encoder that would give us velocity, initial velocity, and a positioning encoder would give us position trajectory, again, latent integration. And then you have a decoder that only looks at the position trajectory, not the velocity one, right? And if you don't do second order modeling, again, like if you remember, we had a latent vector, right? And what was inside the latent vector, who knows? But here you do say that this is going to be my velocity and this is going to be my position. And you do say that time derivative of this thing, time derivative of position is velocity. You specify that. And then that works better if you have limited data and stuff. And then the other thing, this is super nice, it's called augmented neural ODEs. Now here I have two particles, right? And this is like these are my states. And that's like these particles will change over time. And what I want is the blue curve, like the blue dot to go there and the red dot to go there. So this is like the flow that I would like to learn. So in order to learn this, what should happen is that like these two curves should cross. But now this is not possible in ODEs at all. That means like if you want the blue dot to go this way and the red dot to go that way, like once you evaluate the system, like there should be two directions, but this is not possible at all. And if you try to solve this problem, that's what you learn. At the end, like both particles converge to the middle point because that's all an ODE can do. So funny. That's why what the authors propose that, okay, let's not do the modeling in the data space only, but let's put some like extra variables, like auxiliary variables, and then the resulting system would be an augmented neural ODE. Now, this is pretty much the same as a latent neural ODE. I mean, how different? Like, I don't think there's like a major difference, but like conceptually, like this picture should tell us like stuff. And that's a beautiful work as well. Now, if you are learning a normalized flow, like both of these flows, they could give you the same distribution, right? But I mean, the one on the left, okay, left also left for you. The one on the left is much more regular, much more like faster, much faster to integrate compared to the one on the right. So like the authors say, I mean, like they say, like we did normalizing flows, like we trained continuous time normalizing flow, and then we learned this, but this is like crap. And what they do is, why don't we just regularize the Jacobian, right? I mean, we already, for continuous time normalizing flows, we already compute the Jacobian. Let's say like, let's put some constraint that goes like, my Jacobian will be small. That means like the flow will be more regular, like the change will be more, I'm going to say like small. And then they learn this type of flows, right? I mean, it makes perfect sense. And this is like one of the lies that I told you. So again, in continuous time normalizing flows, I told that like you run the ODE system forward to generate particle and backwards for training. And normally these are identical. But now what we do is we use numerical solvers, right? And they have error, but I said that there's like a tiny bit of error. Now let's see. Here the authors show that like if you start integrating from here all the way to time 20, you end up there. And then you start integrating the backward direction. Everything looks good, but like somewhere here and there, like something crazy happens, which is, it is just that like the error accumulates. Like if you integrate long enough, and if you make like a little bit of error in each step, it grows over time, right? And then it accumulates so much that at the end, like these points are supposed to be identical, but they're not at all. And the same for images. Like if you take this image, transform it to a standard Gaussian and transform it back, you obtain this, right? And these are things not many people talk about. And like, you know, like I put all the content, like ugly stuff at the end of my presentation, but these are like quite practical problems. And then, yeah, these authors, they suggest that, okay, let's use this particular backprop technique, which has like certain other like better guarantees. And then that's like the solver that we should have used today. Yes. Now that's a reinforcement learning work where, like, as I said before, like ODEs are actually everywhere. Like if you watch a physical system, if you have like a pendulum system, like that goes like this over time, right? This is like fully continuous. This is like a pendulum problem that like you have this pendulum thing and you want to apply some force so that it, you know, stays upward. And then this is like a quite simple physical problem, easy to solve. But this could be a challenge for RL people, like in certain cases. But in all, like so far the people have been tackling the problem like this. Like this is my initial state. I apply some force. This is my next state. This is like how they view the problem. But I mean, okay, even my motion is continuous, right? But I mean, the simulations are discrete. And here the author said, well, this is wrong. Let's instead of like learning the dynamics in a discrete way, let's use neural ODEs. And then the results look like this. What is going on here is that the red one is the discrete approximation, and the orange one is the true solution, and the green one is the continuous solution. Like if you use a continuous net, and the bottom right is like the thing that you used for solving the RL problem. I'm not going to go into the details, but if you use a continuous time method, then you make much less error. And there's also this thing called neural stochastic differential equations, right? So ODEs are deterministic. That means your differential function, it has always been continuous, but there are certain cases where there is some like hidden stochasticity in the system, right? I mean, why should the particle always follow the same trajectory, right? Like that could be random noise as well. And neural SD or like stochastic differential equations like come into the play. And there is this like line of work on neural SDs where like the first I think 2 or 3 works, like one of them is here, they are quite theoretical, but then later the applications come. And then now people say, well, instead of using an OD net, why don't we use an SD net? And in SD net, it's so that you again have like a bunch of initial values. Here in an OD net, all the initial values, they follow one trajectory and only one trajectory. But in an SD net, you have like inherent stochasticity. That's why once you integrate the system, you would obtain like a cloud of trajectories. Would that be useful? Well, in certain cases. Like if you want to quantify your uncertainty in a way, this could be like one of the ways. And finally, this work concerns GP ODEs, not neural ODEs, where we use a GP to approximate the differential function. And like the nice thing with GPs is that, I mean, they do have inherent like built-in uncertain quantification, right? You don't have to place stupid priors here and there. You don't need like posterior approximation, nothing. What you do is you just say, okay, this is my GP, and then I'm going to integrate that. Like the details are a bit like nasty, but at the end, what you would learn is that here the crosses, like the black crosses are data points, and on the background I show you the GP uncertainty. Like near the data points, the uncertainty is quite small, right? And when you go outside of trajectory, like to the corners, the uncertainty goes up, right? Which makes perfect sense because in a BNN you learn, in a GP you learn small or almost no uncertainty. I mean, let's say small uncertainty near data, and when you go away from data, like it just grows. And it applies here as well, and the predictions are like quite calibrated, you could say. Yes, that's all I have. Thanks for your attention, especially like after yesterday. I thought that today was going to be a bit tough, but I think we made it. Yeah, thanks for your attention, and I'm here if you have any questions. And also you could, I think on the ProbAI website, you can find like a link to my email address or like my website. Feel free to contact with like this stuff, other research stuff, like my PhD is going bad, what should I do type, like all those, like things that I also went through. And like I got like really nice support from my colleagues as well. So like you should also get it. Yeah. Thanks.